Imagine a dark cellar, deep beneath the streets of Sheffield, where the air itself seems to burn. A man stands before a roaring coke furnace, his face lit by an orange glow so fierce it could blind an unshielded eye. He grips a pair of iron tongs, nearly as long as he is tall, and with a single practiced motion, he lifts a white-hot clay crucible from the inferno. Inside that vessel, 34 pounds of molten steel swirl like liquid silver, a material so pure, so uniform, that nothing else in the known world can match it. He tips the crucible, and a stream of glowing metal pours into a cast iron mold, throwing sparks across the stone floor. This is crucible steel, and for over 2 centuries, this scene played out in hundreds of cellars across one English city, producing the finest blades, springs, and tools the world had ever seen. But to understand how Sheffield became the unchallenged capital of steel, we must go back long before that cellar, long before that furnace, to the medieval hills and rivers of South Yorkshire. The earliest recorded reference to a cutler working in Sheffield dates to 1297, when the hearth tax records mention a man named Robertus le Cotelier, Robert the Cutler. By the 14th century, even Geoffrey Chaucer made note of Sheffield in the Canterbury Tales, referencing a blade carried by one of his characters. The town had something no craftsman could buy: fast-flowing rivers descending from the Pennine Hills, perfect for driving, grinding wheels, and surrounding forests that provided charcoal in abundance. By 1600, Sheffield was already the main centre of cutlery production in England outside of London, and in 1638, the first cutler's house was built to govern the trade. Yet there was a problem that haunted every Sheffield cutler. The steel they worked with was inconsistent. It bent when it should have held an edge. It cracked when it should have flexed. The best iron came from Sweden, a remarkably pure product known as Ore-grounds iron. But even after it was converted into steel, the results were unreliable. The method they used was called cementation, and it was the foundation upon which everything else would be built. The cementation process worked like this. Bars of Swedish wrought iron were packed into long stone chests inside a bottle-shaped furnace, layered with charcoal. The chests were sealed, and fires were lit beneath them. For roughly 10 days, the iron sat at red heat, and slowly, atom by atom, the carbon from the charcoal migrated into the surface of the iron bars. Test bars could be withdrawn from the end of the chest to check the progress, and the fires were extinguished only when conversion was judged complete. The entire cycle of loading, heating, and unloading took about 14 days. The result was called blister steel, named for the bubbles that formed on the surface of the bars, where carbon had been absorbed unevenly. By 1720, a Swedish engineer visiting Sheffield noted that the town already had cementation furnaces in operation, and their distinctive conical shapes were becoming landmarks on the skyline. By 1860, there were 250 cementation furnaces in Sheffield, capable of producing 80,000 tons of blister steel per year, and those great bottle-shaped towers defined the city's silhouette. But blister steel had a fatal flaw. The carbon distribution within each bar was uneven. Some sections were hard, others soft. A cutler forging a blade from blister steel could never be entirely certain what lay within the metal. The partial solution was shear steel, blister steel bars that were heated, folded, and hammer-welded together to try to even out the carbon content. It was better, certainly, but still far from perfect. What the craftsmen of Sheffield truly needed was a way to melt steel entirely, to dissolve all impurities, to distribute the carbon uniformly throughout the mass. And that is exactly what a quiet, methodical clockmaker from Doncaster set out to achieve. Benjamin Huntsman was not born in Sheffield. He came from Epworth in Lincolnshire, a man of German Quaker descent who established himself as a clockmaker, toolmaker, and locksmith in Doncaster. His obsession was precision. The clock springs he relied upon, imported from Germany, were maddeningly inconsistent. They broke, they weakened, they failed to keep accurate time. Huntsman was convinced the problem was the steel itself, and sometime around 1740, he began a series of experiments that would change the world. Huntsman's idea was deceptively simple. Take pieces of common cementation steel, place them inside a clay crucible, a small pot, and heat them in a furnace hot enough to melt the steel entirely. Once liquid, the impurities would float to the surface as slag, and the carbon would distribute itself uniformly throughout the molten metal. The result would be cast steel, homogeneous, predictable, and of extraordinary quality. Simple in concept, ferociously difficult in practice. No furnace in Europe at that time could reach the temperatures required to melt steel, roughly 1600 degrees Celsius, and no crucible could survive such heat without cracking or dissolving. Huntsman spent years solving both problems. For fuel, he turned to coke, coal that had been pre-burned to remove volatile compounds, which burned far hotter and more steadily than raw coal or charcoal. For his crucibles, he experimented with clays from the coal measures around Sheffield, blending them with refractory clays from Stourbridge in the West Midlands, a region famous for its glass-making and therefore its heat-resistant materials. By 1751, Huntsman had succeeded in melting steel in a crucible. He moved his operation from Doncaster to Handsworth, on the outskirts of Sheffield, to be closer to the raw materials and the market for his product. His workshop was modest, a coke-fired furnace capable of holding up to 12 clay crucibles at a time, each one containing about 15 kilograms of blister steel, with a small addition of flux to draw out remaining impurities. After roughly 3 hours at full heat, the steel was entirely liquid. The crucibles were pulled from the furnace with long tongs, and the molten metal poured into cast iron ingot molds. The crucibles themselves could be reused several times before they cracked and had to be replaced. What happened next is one of the great ironies of industrial history. The Sheffield cutlers refused to use Huntsman's steel. They complained it was too hard. Their traditional forging techniques could not shape it, and their grinding wheels struggled against it. New machinery and new skills would be required, and the cutlers of Sheffield were not eager to change. For years, Huntsman was forced to export nearly his entire output to France, where craftsmen recognized its superiority immediately. It was only after the Cutlers Company itself intervened, setting up a demonstration steelworks to show the advantages of crucible steel, that the tide began to turn. By the 1780s, crucible melting had become common practice across the city. The story of industrial espionage surrounding Huntsman's process has become legend. He guarded his methods with obsessive secrecy, barring all visitors from his works. But according to tradition, a rival steelmaker disguised himself as a beggar on a freezing winter night and sought shelter in Huntsman's workshop. Pretending to sleep by the furnace, he watched the entire process through half-closed eyes. The charging of the crucibles, the stoking of the coke, the pouring of the molten steel, and carried the secret back to his own works. Whether entirely true or embellished, the story captures the atmosphere of fierce competition and jealously guarded trade knowledge that defined Sheffield's steel industry. The transformation of Sheffield was staggering. Before Huntsman's process, the city produced roughly 200 tons of steel per year. 100 years later, that figure had risen to over 80,000 tons, nearly half of all the steel produced in Europe. Sheffield evolved from a small market town into one of Europe's leading industrial cities, and it was crucible steel that made it happen. Inside the crucible steelworks, conditions were extraordinary. The melting shops were typically built over deep cellars, where the furnaces sat below ground level to improve the draft and concentrate the heat. The men who worked these furnaces, the melters and the teamers, endured temperatures that would be considered intolerable by any modern standard. The melter's job was to tend the coke fire, to judge the temperature by the color of the flame and the glow of the crucibles, and to know by instinct and experience when the steel was ready. There were no thermometers capable of measuring such heat. It was all done by eye. As one Sheffield manufacturer put it with typical matter-of-factness, crucible furnace work requires a special constitution and training. The teamer was the man who poured. He lifted the crucible from the furnace, a vessel now glowing white-hot and containing over 30 pounds of liquid steel, carried it with tongs to the mold, and poured in a single smooth motion. A trembling hand, a moment's hesitation, and the pour would be ruined, the steel solidifying unevenly or splashing dangerously. These men worked in shifts through the night, their faces permanently reddened by radiant heat, their arms scarred by inevitable splashes of molten metal. Above the cellars and the melting shops, the steelworks connected to an entire ecosystem of craft. The ingots produced by the crucible process had to be forged into bars, and from those bars, the bladesmiths and toolmakers of Sheffield worked their art. This is where the famous Little Mesters enter the story. The term Little Mester, Sheffield dialect for Little Master, referred to the independent craftsmen who rented small workshops within larger factory buildings. They were not employees. They were self-employed specialists, each one devoted to a single stage of production: forging, grinding, hafting, polishing. A single pocket knife might pass through a dozen pairs of hands before it was finished, each Little Mester contributing his particular skill. The grinding workshops were among the most dangerous places in industrial Sheffield. Grinders sat hunched over massive sandstone wheels, some of them 6 feet in diameter, driven by water power, or later by steam. They pressed blades against the spinning stone, shaping the edge in showers of sparks and fine grit. The dust they inhaled, a mixture of stone particles and steel filings, destroyed their lungs. The condition was called grinder's asthma, though it was in truth a form of silicosis, and it killed with terrible efficiency. Many grinders did not live past their mid-30s. They knew the risk and accepted it, often with a grim fatalism that became part of Sheffield's identity. The phrase, "There's nowt wrong wi' a bit o' dust," was not a joke. It was a way of life. Now, within this world of crucible steel and master craftsmen, there existed a tradition far older than Huntsman's furnaces, the art of pattern welding. Long before anyone could melt steel in a crucible, bladesmiths had discovered that by forge welding together layers of different types of iron and steel, they could create blades with extraordinary properties. The hard layers held a razor edge. The soft layers provided flexibility, and when the finished blade was polished and etched with acid, the different layers revealed themselves as swirling, flowing patterns on the surface, patterns that gave rise to the legendary name Damascus steel. True Damascus steel, or Wootz, was a crucible steel produced in India and the Middle East, and its watered patterns arose not from layering, but from the crystalline structure of the high-carbon steel itself. But in Europe, and particularly in Sheffield, the technique of pattern welding became a separate and equally revered tradition. A bladesmith would take bars of steel with different carbon contents, perhaps a high-carbon crucible steel alongside a softer wrought iron, stack them together, heat them in the forge until they were welding hot, and hammer them into a single billet. This billet was then drawn out, folded, and welded again, doubling the number of layers with each fold. After 6 or 7 folds, the billet might contain over 100 individual layers. But simple layering was only the beginning. The most skilled Sheffield smiths twisted their billets, carved grooves into the surface before reforging, or combined twisted and straight sections side by side. Each manipulation changed the way the layers met the surface of the finished blade, creating patterns of astonishing complexity, flowing waves, interlocking rings, ladder patterns, and the prized rose or crushed W design. when the blade was ground, polished, and etched in a mild acid bath. The different steels reacted at different rates, revealing the hidden geometry within the metal. A pattern-welded blade was not merely a tool. It was a signature, a statement of the smith's mastery over fire and steel. Sheffield's access to crucible steel made its pattern-welded blades particularly fine. The uniformity and purity of Huntsman's cast steel meant that when it was combined with softer iron in a pattern-welded billet, the contrast between layers was stark and beautiful. The hard crucible steel etched dark. The softer iron etched light. The result was a blade with both outstanding cutting performance and a surface that seemed to contain frozen rivers of light and shadow. By the early 19th century, Sheffield had become a city of extraordinary industrial density. The Don Valley was lined with steelworks, their cementation cones and crucible chimneys filling the sky with smoke. The hillsides above were packed with grinding wheels, driven by the tributaries of the Don, the Sheaf, the Porter, the Rivelin, the Loxley. In 1872, it was recorded that Sheffield had 224 metalworking smithies within the town itself, and another 376 in its suburbs. Every street seemed to ring with the sound of hammers. Every cellar glowed with the light of molten steel. The crucible process remained the dominant method of producing high-quality steel until the 1860s, when Henry Bessemer's converter, and later the Siemens Martin open hearth furnace, made it possible to produce large quantities of steel far more cheaply. Yet for special applications, tool steels, spring steels, and the finest alloy steels, crucible melting continued well into the 20th century. The last cementation furnace in Sheffield was used in 1951. The process Huntsman had invented in the 1740s survived for over 200 years, an astonishing lifespan for any industrial technology. Today, the skills of the crucible melter and the pattern welding bladesmith are nearly extinct. Only a handful of craftsmen worldwide still practice the full traditional process, building their own clay crucibles, firing them with coke, melting steel by eye and instinct, and forging pattern-welded billets by hand. The last remaining intact cementation furnace in Sheffield stands on Doncaster Street, surrounded by low fencing, a silent monument to an age when this city produced nearly half the steel in Europe. At the nearby Kelham Island Museum, visitors can see reconstructed crucible cellars and hear recordings of men who worked the furnaces in their final decades of operation. What was lost when the crucible fires went out was not merely a manufacturing technique, it was an entire culture of knowledge. The melter's ability to judge temperature by the color of a flame, the teamer's nerve to pour 30 pounds of liquid steel without flinching, the bladesmith's understanding of how different steels behave when welded, twisted, and forged together under the hammer. These were skills passed from father to son, from master to apprentice, in workshops that smelled of coke smoke and rang with the hiss of quenched steel. They cannot be learned from a textbook. They live in the hands, in the eyes, in the instincts of men who spent their lives standing before the fire. And when the last of those men set down their tongs, a thread of knowledge stretching back to Benjamin Huntsman's first successful melt in 1751 was, for all practical purposes, severed forever.